I'll go anyway. We'll just charge on. So you're up to week 4, second week with me. The plan for today will be we'll just cruise through end of unit 2 today and then get on to unit 3 for the second hour. I'm going to actually mix it up from the way the notes are organized. If anyone's been proactive and read ahead in the notes, I'm going to jump to some of the more, what would I call it, professional practice stuff rather than the math stuff. So I'll go through Unix and Git in the second hour. So if anyone's been having trouble with GitHub, we'll do some demos and stuff and you can ask me questions. Has anyone actually gotten up to that yet? Are they setting up a GitHub account? Yeah? No problems? Anyone had any problems? Probably a better question to ask. Anyway, we'll go through it. We'll see. Okay, unit 2, that's where we were. Okay, it's a bit of a long unit, so skip through stuff we went through last time. We went through just some array syntax. So I told you about list comprehensions, maps, and broadcasting. Just some nice stuff to learn. And then we went through basically how would you compute a function on a computer? And we did it by, as an example, we went through square root and finding the roots of this function. Just a little bit about types and methods. Just showing you deeply down in the guts of a little hint about what Julia's doing with these macros for code LLVM and code native macros. They will show you what's actually kind of closer to what is happening down at the CPU level. So there's levels to this thing, especially in modern computing. It's like a chain of abstractions all the way down and kind of a hint about how Julia works. I'm sure Claire will go through this with you with more detail about how it actually works, because Claire is like a world expert in this stuff about Julia syntax and how it gets interpreted. Yeah, so just as this thing is like, it gets lowered to this LLVM code. LLVM code gets translated to native code. It's basically how the Julia language was built. And the whole point of this is like, just see that you really don't want to be working at this low level stuff. There's this hierarchy of languages and how abstract they are. And we're in a high level language doing stat stuff and math stuff. You don't really want to be playing around with memory and things like that. When we get into section 3, I'll give you a little bit of a hint about, like, Julia exposes all this stuff if you want to do low level things. Most modern languages will these days. So if you want to muck around with pointers and stuff, we'll show you what's going on. And in particular, when we get to section 3, how things are laid out in memory and the consequences of that when you're working in this high level domain. Yeah, we introduced the Babylonian algorithm. This is based on Newton's method. And we went through the fast inverse square root method. It's called inverse, but it's really reciprocal. So how to calculate 1 on a square root. Cool. Any questions on that stuff we went through last time? Is it all pretty clear? Clear enough? Okay. So this is we're going to start again with a little bit of syntax. And again, there's a million ways to do things. So I'm in Julia. And yeah, lots of ways you could calculate things. So if I say factorial, everyone knows what I mean. So product, so if I do factorial n, it's the product of I equals 1 to n. So if it was 5, it would be 1. So 1 times 2 times 3 times 4 times. But you don't want to be doing that. So luckily, there is a built-in function, factorial, 5. Okay, that says 120. There's lots of different ways you could be doing this, though. So we gave some examples. This one's kind of cool. So I'll just go through, I'll show it on the side. So all these functions, 1 times 2, same as 1 plus 2. These are actually all functions as well in Julia. So there's just some that have a special syntax difference that's called infix versus prefix syntax. So kind of yucky words for a really simple concept. With some overloading stuff. So infix is kind of, it's in the middle of the two things, but you can also in Julia rewrite these things as, it gives you the same thing. So that's the infix versus prefix function notation. So one of the little tricks though that'll be trip you up, it's kind of a little bit of bad syntax. We were talking about broadcasting the other day. So say I have an array data that's equal to 1, 2, 3, 4. I can broadcast, say if I want to add 3 to every element in this array, I could do, where am I looking? Gotten where the guy is, plus 3 data. Oh, it doesn't let you do this in one. They've changed it. I'll change that away. So I'll just do it this way. You do the dot for the broadcasting before the, when you're doing infix. When I was saying about broadcasting the other way, you do it after. So it looks like they've actually changed the syntax so this comes as a parser. In previous versions of Julia, that was the way you defined it. So if I was going to do sign, just to show you what I'm talking about, I'd put the dot after the function name. But if I'm doing plus, I do it before for the infix ones.
It did for me when I did dot plus open bracket 3 and then data.
Okay.
I just swapped this one, but yeah.
Oh, so they've got it consistent now. That used to not be consistent. So Julia's changed under my feet. I'm not cross 110. But anyway, interesting. But just the thing to notice is like it can be a little bit confusing that for these infix notation ones, the dot comes before, not after. So it's a little bit of a weird bit of syntax in Julia that they've changed that order around. I think it's kind of like just an oversight, nothing deep. That's useful. I don't know. Depends what you're doing, right? Like, yeah. Anyway, just as a little thing to show. So anyway, we'll go back to this guy. Another way to do this is if we accumulate times with this splitting operator. So, sorry. Factorial 10. This little, last time I told you that like this special thing is like this iterator syntax. So creates a thing that'll go 1, 2, 3, and it releases this without allocating all the memory. This is the thing you'd want to do so you're not making heaps and heaps of memory for no reason. You can actually splat out this collection. It's called a splatting operator, those 3 little dots, and it will go 1, it'll put them out. So like if you've got lots of arguments, you can put them in like that. So that will splat out times, gives you the same thing. There's this accumulate times 1 to 10. So this is giving you like all the things in order. Like if you wanted to cumulatively multiply them and the last just picks off the last element. So I'm pretty sure this will all get optimized away if you did that code lowered. That would give you the last one. Or you can just do long-winded function thing, which is the example. So like function my factorial. Oh, see if I was going to be lazy and see if there was one there from before. Let's call it something else. Factorial 2. Then we go n. And then you go something really, so what do we want to call it? X equals 1 for I in 1 to n. X times equals I. If I got that right. Yeah, so you can do the long-winded function version, but just different ways to do the same thing, all kind of give you the same result. Really, the whole point of doing that is just to show you a little bit more syntax and some different stuff you could be doing. Some more or less natural. So in a normal class on computer science, you'd probably spend a lot of time on recursion. I'm not going to worry about that too much. It's just like in this level, like most maths people will get the idea that like a recursive definition of a function is kind of a natural thing to do. Just the interesting thing to do is that in lots of programming languages, that's a really natural way to set up problems.
Can we delete a function? Like if we sort of say like created a function with a method and we want to delete that method,
yep.
Is there a way to actually just delete like that method from the function?
A good question. I'll come back to that later. This is, are you thinking like you can redefine things. Structs will be the problem where you'll come into problems. Like if you've set up your own struct, that can be a bit of a pain to redefine those. Yeah, I mean, why do you want it to delete it? I mean, what you want it to be gone?
Yeah, just
Yeah, this is a problem with these REPL sort of sessions. Like the namespace can get really messy. So it's kind of get you to moving more towards making modules, making files you'd include rather than having this thing. Then that's sort of not a problem. But if you're working in like a notebook and stuff, that's normal problem. You just usually redefine them is usually the thing. Not a problem, but structs, you'll have a harder time. Anyway, back to where we were at. Yeah, so recursion is a thing. It's a big thing in computer science. We're just going to go like functions can call themselves. That's all we're going to go for. It's like most languages will support that. Julia is one of these. So you'd notice there's a recursive definition for factorial, where if n equals naught, it's going to be 1. For any other number greater than 1, or greater than 0, sorry, it's going to be itself multiplied by the previous element, factorial. So that we can pretty naturally translate into a recursive function. So we're going to say, basically this little mathematical statement translated into code, we can go my factorial for n. If n equals naught, we're going to return 1. Else, we're going to return n. And we'll notice here that we're calling my factorial with the argument decremented by 1. So it only kind of makes sense for ints, but so we should probably be type annotating that with an int. And we can do that. So let's just do it, just to prove that it's true. My factorial. Go back. Okay. My factorial, if I call it with 0, we should get 1. If I call it with 1, 1, 2, 10. Little bit obscure about what's going on underneath. But, we get the same answer as the built-in one. It's true. So that's the same thing. Cool. So this is we're going to add a little bit of logging to this guy, and we'll just see what's going on. So we will see that what can be a little bit obscure with recursive things, like what's actually going on the inside, it can actually be really tricky about like recursion depth can get really out of control, and it can be a little bit hard to reason about what's happening with the program if you're doing too deep recursion. And has anyone, I guess it's, is it going to say homework question 3? Is that the one? Is the big int one? The big float one, sorry. Has anyone exceeded the recursion limit for that, mucking around trying to get the precision? Has that happened to anyone? That was the first thing I did. When I just like, I'll set it to a big number and see what happens, and you can get it to explode. So that's definitely a thing about how much memory it uses, and recursion depth is definitely a problem. So what we're going to do is just try and see that. So what we're going to do is when we enter the function, it's going to say, I've just called my factorial, this $n is the string interpolation. So it's going to take the current value of n and print it. And then when it returns, so again, remember the last line is the return value in Julia for a function. So if there's no other explicit return, that's the one it's going to get. It's going to go, I'm returning from that call with factorial n. I won't belabor it because you can believe it, but you can see that it's going, if I input this with my factorial 10, it will start with 10, 9, 8, all the way down to 0. Then it gets a value of 1. And then it's returning from here with 0, 1, 2, 3, back up all the way to 10 to get this thing. So yeah, you have a stack trace function if you're worried about that sort of stuff. I'm not going to talk too much about that. But the whole point is here, it's like, can be really natural for some problems to set them up as a recursion problem where you're going to call it, the function's calling itself. That's the big thing. So my factorial is calling my factorial. That's fine. If you want to be nifty, you can do it all as an inline function. So I think I've said this before. My factorial n. So this is a way of setting up, I'm defining, if I put the parentheses around this, it's like I'm making a function. And what I'm going to do is I'm going to say n equals naught. So this is a predicate. Is anyone familiar with ternary syntax? Has anyone seen that before? A couple of people. This is like, it's called a ternary because it's a function with 3 things, but it's a really useful syntax to go like, what you usually do is you put a predicate, or a Boolean thing, a function that will evaluate to true or false. And then what does it do on the true condition and what does it do on the false condition? So if, it's basically like saying if n equals 0, I'm going to return 1, else I'm going to return n times my factorial n minus 1. So works. So that's just a compact way of writing it though. Like underneath, I can do this long-winded thing. So my factorial, call it my factorial 2. This, you know, they're syntactically different, but they're actually going to do the same thing underneath. So it doesn't actually change anything. You can do this as an experiment here. Let's just see what it does. Code lowered, my factorial 10. So we've got this and my factorial 2. So if you go through this line by line, the lowered code, go to 3, if not y, return blah, 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 main my factorial 2. Oh, I probably called that. Let's just, did anyone see my bug? I was actually calling the other one if I didn't change that, but I'm lying to you if I say that they're exactly the same. So that one and that one. So this one's going code lowered, blah, 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 blah. The only difference is the function name. So this one's factorial 2. It actually lowers down into the same machine code. Same machine code will get executed for those two different function definitions. So Julia's smart enough to go like, this is what you should be doing given what you wrote. So there's no difference in what it's doing. It's just how it looks. And so sometimes it's really nice to have these nice little inline functions if you want to write it nice and compact. Sometimes it's just confusing and you can push the definition of one line too far and you render something really, really confusing and people won't like you very much. So they're basically doing exactly the same thing. That's what I was trying to get there. So, question, has anyone read the notes ahead, knows the answer before I ask? How big do you think we can do factorial? Like, how big before it's going to start to panic? What's that? Depends on your RAM? Well, maybe it depends on your type. Like if we're not using a big, if we're just using float 64, I'm sorry, in 64, how big before we run out of 20? We've got to vote for 20. Anyone else? 30? Yeah, it's a not very big number. So that's, yeah, so if you go big, it's like, yeah, cool, you can go really big. But in 32 or in 64, this might be a thing you want to check. Anyone come across Stirling? Who's done StatMech stuff or statistics, maybe some combinatorics or something? You've done Stirling's approximation, you've seen that before? So like, it's a really common thing. Like, I think it came up in the first lecture. I was going like, you know, how many ways could you rearrange this string or this array? When I was saying about like counting the next one, it'd be n factorial. So it's like, you go back 200 years or 150 years before you had a computer, how do you actually approximate that for a big number? Like if you're doing thermodynamics or something where you go like, oh, cool, there's a mole of gas or something, you know, like 2 to the 24 or something, atoms bouncing around, and you need to take that factorial. That's a big number. So there's this old school approximation, Stirling's approximation. Yeah, it's kind of a weird one. It's interesting if you read up about. I won't talk too much about it though, but basically it's a way of approximating if it were a real number rather than worrying about this factorial thing. It's like, let's just do an approximation and we can do something to calculate with it. What's that? Yeah. Yeah, so we'll do, so basically first a little bit of code here. I'll just go through this. Let's just copy it out and we'll go through the code just to see what we're doing. Maybe it's hard to see that. Just make that a little bit bigger. So we've got this list comprehension thing again. So we've got it all in square brackets. And over on the right-hand side, we've got this for n in 1 to 10. We're going to make a tuple. So tuple, everything, collection of 3 things. And what we're going to do is these are a named tuple. So we're going to say n factorial equals 1. And we're just calling the normal built-in function for n. We're going to go n to the n and the ratio of n on n to the n. So it's basically like the leading order term of this guy is this thing up here. It's going to grow the quickest. So we kind of want to see how this approximation's going. And the ratio gets small as it gets bigger. So like the difference between n factorial and n to the n gets small as you get bigger. So blah, blah, blah. Don't think that's so interesting. The more interesting thing is a bit of syntax here. So I can go a equals 2, 3, b equals 6. So that's a thing called a name tuple. Type of name tuple, and it's got two names. One's called A and one's called B. So if I wanted to set this to a variable, x.a, and you've noticed that last time I was talking about structs and getting at the bits of structs. It's the way you can get this stuff out. You can go a.b, blah. That's, you can access these things like that. That strange just overload of syntax here. We're going n factorial is the first one of these name tuples in this list comprehension. Second one's n to the n, which is n to the power of n, and we've got this ratio. So hopefully you can see what that's doing. This is all just a bit of propaganda to show you for small ones that Stirling's approximation sort of gets good as you get big, but I'm not going to talk too much about it because there's a bunch of things going on there that's less interesting. So basically the whole idea is, we go back here, that n factorial approximately equals this funny expression. And we've just done a little demonstration that in the notes that, you know, it's a reasonable-ish approximation showing it's converging. So we can just plug this in as if it was a float and see how big, you know, how big if it was uint64. So type max uint64, can't type, it's always a problem. Typo max, that's like making fun of me, actually. Type max, and you know, this has come out as this thing, so it's some big number, 2 to the 64 minus 1. Oh, didn't like that, so big. Oh, no, what am I doing? Got it here. So 2 to the 64 minus 1, type of this is signed. Uint2, blah, 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 blah. Yes, so that's what I want. I don't know why I'm having trouble with that. Uint2, but then, yeah, so sorry, print. So that's a very big number, and that should be type, that's just the same, sorry, 2 to the 64 because it's 64 bits. One is the special one for 0, so 2 to the 64 minus 1 is going to be the biggest uint we can have. So again, useful type function type max, but if we plug this into Stirling's thing, so type max equals blah, while Stirling n. So let's go back to that. So we've got a little function. There's some useful things here. I'll just go through this again. Just don't want to spend too long on this one, but so Stirling's approximation for 10. And again, we said factorial 10. So that's a smallish number compared to the size of factorial 10. So small fraction of that, gets smaller as you go bigger. Basically, you just want to do, when does Stirling's approximation exceed, when does it exceed the type max? So we've got a little loop here, going to go through. If Stirling is greater than the limit, so we can just do this by hand because it's not actually that big. I think someone had a really good guess. Oh, less than, sorry. Stirling 20 and 21. So that changes over at exactly 20. So you can go through it in a loop, evaluate this thing. When does it exceed this limit? So it's actually surprisingly small. So you have functions that will come up in mathematics all the time, particularly if you're doing stuff like statistical mechanics, combinatorics, probability, all the time, where you'll get very, very big numbers. You got to come up with a way to deal with them. So we can validate this factorial 21. So it's going to say, it comes up with a nice error. Overflow error 21 is too large to look up in the table. So who wants to have a guess at how factorial is implemented? Yeah, they're just looking it up in a table. So if you could do this at which thing we were talking about last time, factorial for an int, should be able to go look in base combinatorics. And I bet you if you go there, somebody else can do this after the lecture, but it's just a lookup table because like there's not that many. So you may as well just make a lookup table. So when I was talking the other day about like doing square root, like having lookup tables at values and interpolating in between is a completely valid way to do lots of functions as well, particularly if you know like it's on a periodic domain. Just, you know, it might be faster sometimes to make a lookup table and more accurate to make a lookup table and interpolate. So lots of options for what's going on. This one's a really dumb one though, because there's just 20. Just type them out by hand. Hope you don't make a spelling mistake. I definitely would. So hopefully this has come up. So you've got a homework question about big. Has everyone played around with this already? So it's like preaching to the choir and boring. You don't need to know about it anymore. Big is like, you can do stuff in software to deal with bigger than that. So bigger than what you're allowed to represent in floating point. So you can make big 10 to the 3, go factorial, 10 to the 3, and it'll make a bunch of stuff on the screen. Who's an anarchist and wants to see when it'll break, like 30? No, out of memory. So someone asked the other day, like, you know, big is like, how big can it actually be? It's like, there's a way to test it. Try and take factorial of 10 to the 30. You run out of memory. Another question for anyone who's super keen is like, if you wanted to find out where factorial for big would fail, like when you run out of memory for a given amount of memory, you can go through the same sort of analysis, dodgy analysis, and figure it out. They would go like, I'm trying to allocate more than you've got, because it like if you try and allocate more than you've got, depending on which system you've on, like if I'm on Linux, there'll be an out of memory killer that would just go smack and my program would disappear. So normal thing when I'm programming day to day is for the OOM killer to just come along and I'm doing something silly. So yeah, so this would be a bit more clever than that and go like, you're trying to allocate more than you've got, please, error, don't do that. Again, if you trace through the source code, if you use that at which thing, you could probably trace through where in Julia this is happening and find this thing. So see if I'm lying to you or not. Cool. Okay. Yeah, this might be useful for you if you're going to try and print out digits and stuff, but I won't say too much about that. Coming up with homework stuff. So mathematicians like to abuse concepts. So does factorial of 6.5 make sense? Does make sense? Kind of, sort of. This is a normal maths trick, especially as you're going up in levels. It's like you take something that's sensible and then go, what does it mean if I take a derivative to a fraction or something silly? Like in some sense, it'll make sense. Similarly for this, if I try and do this, Julia will go like, nah, can't do that because the type of this is wrong. Again, if you see this error, when you see this error, I should say, most common error you'll get when you're programming Julia is you'll get this method error. No method error matching factorial float 64. That means the type of the thing you're passing to this function is it's unhappy about. And it says, well, I know how to do uint 128. I know how to do int 128. And I know how to do it for big float and some other stuff. So, but you're out of luck for reals. So floating point numbers, I don't know what to do. So long time ago. So this is kind of interesting because I'm like, I'm old, but I'm not that old. When I went to uni, the people who taught me at uni, they would have done a course on special functions. Has anyone heard of that? Is that like back in the days of your stuff? So someone who's like maybe 15 years older than me, they would have, when they went through uni, they probably wouldn't have done a numerical methods course, but they would have done a course on special functions. And there's a zoo of these funny little functions like this, like gamma function. Has gamma function come up for anyone before? Yep, in combinatorics or something, big numbers.
Yeah.
In statistics for sure, yeah, because it's like this nice, again, it's like a nice approximation or nice extension from the integers to the reals for something like a factorial. But this guy, gamma function, is kind of like this thing. So if you want to use it, you're going to have to include special functions. Yeah, if you don't have it, you'll have to do the package add stuff. Not much magic there. Then you can do gamma. Let's see what syntax is going to want. So gamma 6.5. So that will give me an answer that's kind of like basically like extending it to the beyond the domain of where it was factorial makes sense. And okay, again, so again, how do we, this has got a definition in terms of this funny integral. So it's an integral from going from 0 to infinity of x to the z minus 1, e to the minus x dx. And I guess, has anyone done a course on numerical methods yet? So how would we actually take an integral numerically? So last time we were going like, cool, we're going to find a zero by going like derivatives, kind of like the slope at a point, and then we'll solve for zero. How would we do an integral? Yeah, that's right. So the Riemann sum is like, you know, when you're doing your first year calculus, you'll do this like, you know, I'm going to cut it up into boxes and I'm going to shrink the boxes. If I sum all that up, that limit is kind of like what an integral is. So we can just do that on a computer and that's like going to work as well. Not a universal procedure for doing integration. It's like, anyone come up with a reason when this is going to fall over really hard? Yeah, if it goes to infinity. So same, I guess, Lebesgue measure theory and stuff, like same things where you're going to have problems with, you know, have some wacky function that's got a singularity in it. You're going to have to do something about that singularity. So not a universal procedure, but a good enough procedure. So what we've done in the notes, I'll just get back to it, is we can just do this grid. We can make a grid. We can make the integrand, and we can just sum this over the grid. And let's do it. I don't think there's any syntax there that's interesting for you guys. So my crude gamma minus gamma. It's like, it's pretty crude. So what can we do to make it better? So we've got some options. What might be some options? How are we going to make it better? If we want this to be closer to the actual value. So Riemann sum, how do you make it closer to the actual integral? Take smaller steps, more steps, smaller steps. So we also want to go, so when you look at this function definition here, yeah, we've got to go to infinity. So you'll see here, we've made this like canny approximation of like 50 is like infinity. That's good. So it might not be the best thing. So hopefully if you play around with this, you make it smaller. So there, that looks a bit better. So that's down at like floating point stuff. So 10 to the minus 11. Whereas if we had the default arguments, it was actually kind of crap.
It's
Oh.
the first
Did I messed up. Oh, it's actually, yeah. So maybe try it the other way. So if you make it 2 course, there you go. Starts to break if you make it 2 course. So I thought the notes were cleverer than they are, but no. So yeah, you got to put some thought into. So there's not, again, this is kind of like a little teaching point as well, is like not immediately obvious how you should be setting the discretization and the bounds to make this kind of be a good approximation. It's kind of like, there's a little bit of heuristic and a little bit of playing there to get it to work. You can do the analysis more rigorously, but it gets really, really hard, really, really quick. So we'll talk more about that later though. Cool. So why would the gamma function be considered as this? Is like this recursive definition. You can see, if you turn the crank, if I define this in terms of the next element and I do integration by parts, do all this stuff and sort it out, you can see that this recursive definition holds similarly to factorial, where you're going to go like the n plus 1th equals z times the n minus. And it's kind of annoying how we set that up because we've said plus. Whereas back as the definition of factorial, all the way back up the top, we've had this recursive definition where we go like, oh yeah, it's like n minus times the previous one. So we have a similar definition for the gamma function. If you turn the crank, you'll see that's true. Okay. Yeah, so just below. That's a typo. That's why I wanted to go back. So they keep meaning to, anyone wants to do a pull request on the notes, we've got a typo there. So it should be, this should be n minus 1 factorial here. Yeah, just to be a little bit confusing. And just to complete the argument, if you do the gamma for the value of 1, you'll get 1, similarly as that recursive thing we did before. So, what are we doing? Let's not worry about that. Gamma thing's a bit more wild though. So if we do gamma, what's the special spot? If we sneak up onto it, it's got values all the way up to -1. But then if we try and evaluate it at precisely 1, we get an error. So there's special spots for this function that are going to be a bit nasty. So again, as I was saying, you know, not a universal procedure to do this Riemann sum and hope you're going to skip all the singularities. Like, got to be a little bit careful. So interesting exercise for you guys if you want to go and look up how the gamma function's implemented. I'm sure this is actually quite sophisticated how they're doing it. It's not going to be something dumb like I did where it's just do a Riemann sum and it'll be good enough if you set the limits. Yeah, so here's an example where we're going to use plots. I'll just copy this code across. Give you some syntax for driving the plotting libraries. Has anyone been playing around with the plots and stuff yet so far? Had to do anything for the assignment yet?
I think the exercises or our tutorials we already plotted.
Yeah. So plotting libraries are a nightmare. Are you using, have you been given advice to use Makey or plots? I think all the notes we use plots, but Makey's probably better to use these days. But anyway, plotting libraries are definitely a thing to learn, particularly when you're doing assignments, because it's part of the presentation aspect of like how to drive these things to make pretty looking plots, label your axes. So what we've given you here, we're just evaluating the gamma function. So what we're doing is we've set up Z. I think I copied that across too quick. So this is a little bit of a tricky trick. So Z set diff -3, 0.01 to 4. And we're doing the set diff with the negative integers over that range. So that's basically just going to cut out all those nasty points. If we didn't do that, what's going to happen? Ooh, wasn't happy. So the main error with -3, nan result for non-nan input, stack, blah, 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 blah. Didn't like it, and kind of a nasty error message. So the whole point of doing this set diff stuff. Oh. Set diff, so we've got -3 to 4, -3 to 0 as integers, just to be clear. Collect. So set diff will take those elements, suck them out. So when you try and do the broadcasting, it's not going to fall over on you. We've got, this is like the hard thing about plotting libraries. And I'd say the plotting libraries for Julia are kind of poorly documented. So this is going to be a bit of an adventure when you go to do it. You can set the Y limits. You can set a legend. You can set the Z label. You can set the Y label. And you can guess, you know, you can put the latex stuff in the plot. So look kind of pretty. Yeah, I don't know if there's much more to say about that, but that's just the weird little bits of syntax there. And this is another example of a mathematical function. I guess the interesting bit for me is, you know, factorial scaling is bad. We'll come to that again as soon as well. When we talk about algorithmic complexity, it's like anything that's factorial scaling is like trouble. Yeah, there, again, like last time we used, we use Newton's method to try and find the roots of a function. That kind of seemed to work. And here we've done we've gone to another mathematical definition to derive an algorithm where we're going to go if we want to evaluate what this function is, it's defined as an integral. We can do a numerical quadrature method by just go to the definition and go oh, it's a Riemann sum, shrink the bits to go as they go to 0. You can get a reasonable approximation to this thing. And little bits more of syntax. That's Stirling's function and gamma function. Any questions on that bit? Happy? We'll move on. Charge on. Strings. So we've done a little bit about strings and chars. I think I brought this up before. So if I go, I'm going to go, could just copy the notes, but that's kind of boring. So if I just go x equals A, B, C, D, E, F. Okay, so type of x, we talked about this before, is a string, but strangely enough, this is kind of like a thing you can index and it makes sense. So if I get the first one, I get this other thing back, and this thing back is not a string. It's actually a type char. Char. So the elements of a string is, you can think of a string as like an array of characters and of this type char. So we did the size of, again, character encoding. This says the size in memory, if you want help. It's canonical representation of a data type. Size in bytes. So this is in bytes, so 8 bits, if you're going to get this one, of a binary representation of a given data type. So if we wanted to do size of x, it's going to be 6 because it's 6 long, the same as the length. Oh, if you can type. 6. So each character is a byte. You can do this stuff if you want to do some funny syntax. Just again, so same, we go like, for strings, the concatenation operation is different to Python. Yeah, you multiply to get these guys stuck together. And again, you know, if you want a space, you have to put a space in because a space will be a special character as well. Funny little demo in the notes is like, if you want to take the power to the 4, I don't think I've ever tried to do that before, but yeah, you'll get something that just concatenates these things. So like, repeat, it's a bit of an abuse of notation, I would say, like, but to do the power is like multiplying 4 times in a row. You get 4 versions of that concatenation. There's some stuff to know that's kind of boring, but I'll talk about it anyway. So the base alphabetic characters are called, in this encoding, called ASCII. Again, we were talking about integers. You could choose any representation. There's a particular one that makes sense. This is one that was designed by a committee, and an American committee, because they got there first, I guess, where they've decided that particular patterns will represent particular characters. And annoyingly, there's like printable characters start at 32. So the first 32 don't come up as anything. So you go, let's see this. So we're just going to go through this guy. This will print out that table. So we're going to go in, what are we doing here? We're going from 32 in hex up to some other number, and it's going to say these are what all the characters map to. So 20 goes to a space, then exclamation mark. The actual numbers start at 30. Uppercase starts at 41, and then you get lowercase later on with an offset. And a bunch of other useful characters. So that's just an encoding they've chosen up to 126. I don't know why they chose to do. We can just go for the first few, and you'll see there's a bunch of nothing, whole bunch of nothing up to until you get up to 32. Oh, I don't know what's going on there. Some Unicode weirdness, but yeah. Yeah, so that's ASCII. Yeah, things to know is like a char is not a string. So if I go, what's the prediction on what that's going to do? false. But yeah, so yeah, I'm trying to see what they say. If I do the first one, what's that going to be? True. Yeah. So, you know, a string is an array of chars. And because they have an integer encoding, I can add to them and then I'll get the next one in the thing. So really underneath, it's just an integer, a UN. So I can add to them. So think maybe it's the kind of thing is like we saw there was a fixed offset between uppercase and lowercase. So if you wanted to convert from uppercase to lowercase, what do? You just add the offset. It's like pretty boring, not super exciting. Yeah, cool. I think I'll talk about this one and then we'll really quickly and we'll take a break. So I don't know, do we have anything on JSON parsing in the homework? I can't remember this year. You got that? Come across JSON before? Anyone know what it stands for? Object notation, I think it is. So it's like a name that's non-descriptive. It's just a special type of text file. Parsing it can be a bit of a pain. So there's a library for it. Oh, I didn't add this stuff before the lecture. Naughty me. Yeah, so HTTP request library and a JSON library. So I'm just quickly going to install those and hope nothing goes wrong. What we're going to do is, I think you guys have got driving an API as one of your questions for the LLM. You got to kind of talk to an API and get it to give you stuff back. It's like APIs, I even forget what that is, but basically it's like an interface, programming interface, application programming interface to a thing. Usually, like when people talk about it, they talk about HTTP APIs, which is like doing it over internet protocol. There's a request, like in Python, the equivalent thing would be the request library. In Julia, it's this HTTP one. What we can do is we can do a GET request to this web address, and we can get this thing called Shakespeare.txt. Hopefully this is finished now, and I'll just show you that. So just a baffling world we live in where we can go, in a lecture, we can just go blah. And without waiting too long, hopefully, Julia startup overhead, because it's probably going to be the first time I did this, so it'll take a bit longer than I expect. There. So I just downloaded Shakespeare's LifeWorks, like with Julia startup overhead. Data has all of Shakespeare in it, so it's crazy. So this thing, type of data, is a HTTP. So to do with this package, they've made their own struct, and they've made their own like little nested thing where it's like HTTP messages, it's a response type, this struct. And so we can have functions that we can do with it. Basically, we can turn the body of this thing into, saying there's some things, there's a body, there's headers, there's a request, there's a status. So if I was being a good programmer, I'd check the status of my request, because just because I asked for it doesn't mean I got it. I could have got junk. So everyone's seeing internet errors like 404s and stuff. Like you should be checking for that. Does everyone know what 200 means? 200 means good. So what I can do, dot body. No, yeah, I want to string that. So cool. That's a thing. Oh, I think I'm going to be in trouble. I have to do this again. Shakespeare. Yeah. So if I do it, this is kind of an annoying thing about this one. If I do it twice, it's gone. So I only get it the first time and then it's gone from the message. So I have to do the request again. So there. That's just for the interest of me being an idiot. I want to check how long that takes to download all of Shakespeare off the internet. So it takes 0.8 of a second, 0.08 of a second. Then we can go Shakespeare equals string, and we've got it all as a string now. And split is a text parsing thing. So before I had this, hey you, common thing you want to do with strings is you want to split it on like a space, right? And then I'll get a thing that cuts it at the space if I want to get the bits out of it. So when I'm doing the next line here, Shakespeare words, if I split this thing on a space, I'm going to turn this string into 900,000 words. That's what's going on. What are we going to do here? So going to do a different request to some. So I think this is Yoni's textbook about statistics for Viola. It's got some JSON words. And we can use this to get some keywords. So it's going to make a little dictionary of like common words that you might be interested in. So that's the other thing we got from the request. So normal thing to do would be like this kind of word count thing. And I'll talk a bit about why. So this is just a demo of like playing around with JSON and stuff. So we're going through the keywords, Shakespeare words, and if it's in the keywords, we're going to count up how many times it occurred. Cool. Just as a thing to do, just so you've seen HTTP requests and JSON and parsing. So you go, king turned up 1,698 times, blah, 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 blah. Cool, and you could sort that, all that thing. So I think this is kind of interesting as a demo, and I'll talk a little bit about history of like, early internet didn't work for many, many reasons. And I guess depending on how old you are, like a thing, spam was a huge problem with email when it first came out. Like basically you're at a point where like most of the email is junk. Like it's just garbage that someone's trying to fish, you know, trying to get you to click on things you shouldn't and all that sort of stuff. So it's kind of like you're in the world of natural language processing actually working now. So like LLMs are kind of amazing in the last couple of years. Very, very back in the early days, a really simple thing you could do was just doing this sort of dictionary lookup and word frequency to calculate what the content of a document is. So I think this is like a cool bit of like early internet stuff. I'll just talk about it. We took the machine learning out of this course, but I'm going to bring it back in because I'm the machine learning lead at my work. So how would you like, it's kind of like you want to do a calculation. You want to go like, what's the probability that this thing I'm looking at is junk, like it's spam or it's Shakespeare, given a whole bunch of words? It's like, that's not a super simple calculation to do because you like the words, they can, first problem is going to be like, doesn't matter how long this message is, all the messages are going to be different lengths. And like that doesn't kind of change the probability that way. And you have to sort of encode a message into something you can actually do a calculation on. So one of the early applications of this stuff was applying Bayes' theorem. If I say Bayes' theorem, you guys should be kind of happy with that. So the setup would be something like, what's the probability that this thing is a spam message given some feature of it? And so what the initial spam filtering algorithms, the first wave of them that actually kind of worked was to do something very similar to what we were doing here, where they would just go, if I get a collection of emails and I'm going to go, what's the 1,000 most common words that turn up in these emails? And that's that dictionary we're counting against. You'd build up this dictionary. Then for every message, you would go like, what's the frequency of this word turning up in this message? And then you suddenly turn, your abstract message into this thing where it's just going to go like, this word turned up this many times, this other word turned up this many times, this other word turned up this many times. And if you can believe it or not, this gets a little bit complicated. This gets a little bit complicated if you've got a complicated feature vector. So they just assumed independence for every frequency of the thing turning up and just multiplied all the probabilities together. And that was kind of enough to cut out like 99% of the spam. And suddenly email works, and then you have the internet boom in the early 2000s. Like this stuff just started working. So this really, and you can kind of see that with Shakespeare, like if you had things like, if your random text document, how often would king and prince and hell and stuff turn up? You can sort of see it in the frequency of Shakespeare. It's probably much, much, much more common than just like a random bit of text. So that's kind of an early application of this sort of technology to the internet. Oh, Prince Denmark, Shakespeare, Prince Nigeria, spam. You got it. Okay, I'll take a break there and then we'll start on section 3, I think. I think I finished that guy. Cool. Oh, okay. Start again. So finished unit 2. I've got these all offset by 1 in my head. So I've got an off by 1 error. Last year we didn't have the bootcamp bit. So everything I think of as unit 1 is unit 2 this year. So if I say the wrong thing. Yeah, on and deeper. I'm going to mix it up though. So I think I said this at the start of the lecture. I'm going to jump to the end and do more stuff on tooling just to make it easy for people who you're coming up to the homework stuff. So learning a bit about GitHub and stuff will probably help more now than learning about sorting. It's kind of stuff you can sort out on your own. So the point of section 3 is going to be, we've gone about basic data types. We talked about ints and uints and kind of waved a hand at floats and showed you a struct or two, but not really. We're going to go a bit deeper into the algorithmic stuff on this one and basically, and data structures on top of that. So there's kind of 2 bits. We're going to talk a little bit about algorithmic stuff and analysis of algorithms, and we're going to talk a little bit about some data structures that are useful and more about some higher order things like how arrays are laid out in memory and such. But I'm going to save that for later. And we will jump to the end and come back unless we happen to do super quickly through this stuff and I run out of time. So basically tools, I'm going to start with some Unix stuff, command line stuff. I'm not Nix-Fu expert, but I'll try my best for you guys. Git and GitHub is probably the one you're going to get most confused about. I think most of the other stuff is pretty straightforward. And basically, we'll talk about VS Code because it seems to be the dominant one at the moment, but these things are all fickle in computing. You wait a year, it'll be some other thing. Wait another year, it'll be another thing. So these things come and go. They're all kind of the same. So I think I asked this question at the start of like, who's on what? Is anyone on a non-Mac? Is anyone like using Linux again? We've only got a few down the front, a couple of people on Macs, Apple, and most other people are on Windows. So does anyone actually use command line much in Windows? In Windows, you're brave. It's not a great experience, but Unix family stuff is kind of like where it comes from. So basically this idea of like, where do I want to start with this one? It's got to think about what I want to say. So it's completely possible to not have an operating system. So you'll encounter devices like, I don't know, I can't say this because I actually know watches and stuff actually often have an operating system these days. I know someone who worked for Wahoo, if anyone's into cycling, and their little Wahoo, one of their little things was actually just Android underneath and they got it all on top. So that's kind of interesting. But yeah, so totally possible to have these little embedded devices. They don't actually have an operating system. The most common place you'll come across them I'd say if I'm guessing for you guys, would be like in musical instruments and things like that. Because sometimes having a real-time requirement, like one that comes up for me is like synthesizers and stuff. Like often you don't want an operating system that's going to make you wait because you'll have a jitter between when you press the button and when the thing happens. So there's kind of like this non-deterministic thing. And if you want to not have that, there's a whole world of microcontrollers and stuff that don't have an operating system. Operating system is what you're most used to, I would say, on a computer. And it's this thing that's kind of, it's driving all the hardware. You're out here in the user space and you're going to interact with that thing. And it kind of manages all the files and memory and which programs are running and threading a little bit and input and output and networking. So all this HTTP request stuff I just did, it's got to talk over a network and connect and deal with all that stuff. That's kind of a big deal. And the classic one is this Unix operating system. And it's like, it's as old as the hills. It's like, so they all derive from AT&T Unix, which was back in 1969. So AT&T Bell Labs is pretty famous. Has anyone heard of that? If you want to read some history, read about that. It's like so many Nobel Prize winners working there. It's kind of crazy, all the stuff they did. They had a natural monopoly on the telephone network and they hired all the smartest people. Probably a similar situation now with the big internet companies, just having a natural monopoly and making lots and lots of money and hiring lots and lots of smart people and doing stuff. So for good or worse, it's kind of probably just bad. But this idea of they used to have these mainframe computers. So this is back to when computers were the size of a room and really, really expensive. And It used to be you wanted portable code was like not a thing. It's like it was compiled for that code. So I talked a little bit about assembly. Assembly is instructions for a particular architecture of CPU. Back in those days, it was like completely possible to have different architecture for every different one. And so like you wrote your program at one place, if it was in assembly, you couldn't take it anywhere else and use it anywhere else. So they kind of wanted to go up in this hierarchy of like, I want to write things once and then use them in lots of different places. And that's kind of been a goal for computers ever since, and no one's ever quite achieved it. So even in Julia, like I have problems like building things in Julia and then trying to run them on a different computer if there's some hardware component that matters. This still pops up these days. So it's not as portable as you'd like. Yeah, Unix is the ancient one. And then there's kind of a family tree of where everything came from. So there's like, it's also kind of funny. Oh, don't know how big it'll let me make it. They used to just share code. Like we'll talk a bit about software licensing maybe in this lecture too, if I don't run out of time. But they just used to share code and give it to each other because it was like not thought about the same way as these days. So they kind of copied each other. They branched off into different things. And then there's like different families ended up in different spots. And by some magical coincidence, I think this guy's the Mac OS family. Started, if you trace this family tree back here to this unnamed one, you get the Mac ones. Linux is actually kind of a thing off the side. It started as like I think it was Linus Torvalds' master's project. It's like there was a thing they had called Minix and he wanted to make a copy of it and then it got out of control. That's where the Linux family, so they're not actually Unix based, they're Unix-like. So when we're talking about the Unix family, we'll kind of include Linux, even though it's not Unix based. But Mac OS, through this next step and all these crazy things Steve Jobs was doing back then, all trace back to this stuff happening at AT&T Bell Labs back in the 60s. FreeBSD is one you'll come across maybe if you're a computer nerd. And then there's some stuff that's kind of like Solaris and stuff I think they're talking about over here that kind of less relevant these days. That kind of disappeared a bit. Yeah, so I don't know if I had much of a point there, just saying like there's this thing called Unix and yeah, Mac OS has a direct lineage to it. Linux has a like superficial lineage to it where they're kind of like trying to copy the interface. Yeah, and these things like when they were first doing it, it was like, it wasn't one computer for one person. Like now it's like in my day job, maybe it's like, if I'm feeling lucky, it's like 1,000 computers for me because I'm trying to do a calculation. Back then it was like one computer for 1,000 people and they'd time share it and switching in and out. So this idea of needing an operating system to manage that. So like I'm running several different programs on this thing and they're all running at the same time and the computer needs to kind of make it seem seamless to the user that these things aren't really happening one at a time in serial, like they kind of are at a low level. Kind of want to make it seem like like it's all smooth and you can run as much as you want to. That's kind of the job of the operating system. Linux is Unix based. It's like kind of based off that by Linus Torvalds. It's been that one, yeah, in server land, like if you're a professional software developer, depending on the type of work you're doing, my day job's all Linux, 100%. I haven't actually used Windows in a decade and a half. So when you guys come up to me and ask a question about like, oh, I tried to install Git Bash, I'm like, yep, that would be hard for me too. Windows is not Unix based. Yep. You got this thing called a shell, command line interface. It's kind of, there's some funky names for this stuff. Control Shift plus plus. It's funny names is like, there's the kernel, which is the inside bit, and then the shell that kind of goes around the kernel, and you're sending things down to it from here. So the most common one you'll see is a thing called bash. You heard bash come up in this course already. That's this guy. That's what I'm using here. There's different flavors of this though. This is the command line, and back in the old days, you'd be typing stuff and sending commands. And there's like a base set of commands that we'll expect you to do. What do we want to do? So most common one, you'll come into a terminal session and you go ls is like for list. What's the content of my directory? I've got here, if I'm in something, okay, cd, I'll go back to the bottom. So this is my home directory. I've got a bunch of stuff there. There's some random stuff on this computer. I tend to keep all my stuff in a boring place called source. And in here, you'll see, is that showing up well? Can you see that blue? Is that reasonably visible? Conscious of anyone who's got issues with color blindness or something. You see there's a bunch of repositories here. I've actually got this course here as a repository. Programming course for Julia. So if I want to move around, I go CD and then into that folder, then ls, and then I've got the uni notes and stuff here. So cd dot dot cd silly test repo. Okay, ls. So they're kind of like some really basic stuff is just ls cd for moving around. If you want to go down a level, 2 dots, that's for this one. Back up to Paul's silly test repo if you want to go down more than 2. Then back to home. And yeah, that's basic navigation stuff is that. Really common one, I just keep checking notes, is PWD you might want to do, which is for print working directory. So that will go like, where the hell am I? I'm at home, Paul Billette, source, Paul's silly test repo. Yeah, that's the basics of navigation around the folders and files in a system. You know, you'd be used to in, you know, these guys, there'll be some version of this now, like in all Linux systems, like basically the same as doing this clicky programming course with Julia. I'm getting to the same spot. So it's a text way of doing the same sort of interactions. And that's okay. That's pretty boring. LSCWPD. So when I'm in this guy, say I've got a file like this readme.markdown. Something I might want to do is to have a look at that is cat readme.markdown. It'll say Paul silly test repo, blah, blah, blah. Not so interesting. If I go, that's terrible, I want to get rid of it, I can RM to remove it, and then it will go away. What's that? Cat puts it out as like an terminal output. I just deleted it, so I can't show you. You get a Git demo. Oh. Okay. Sorry, a little bit of Git coming up before that. Cat will be basically like, it prints to the output line by line, whatever's in this text file. Cool. So, you know, everyone is a bit postmodern these days. You'd look at it in a code editor. You'd go, oh, it's Markdown. It's coming up with a bit of formatting stuff, blah, blah, blah. If you just want to see it in the terminal session, like say you don't have a visual display, you've just got this terminal thing, you can cat, see what's in there. Another useful one for looking at this stuff is head. It'll give you, say if you are moving to a bigger file. Let's see what I got here. See if I got anything. Do it with that. CD source. Sorry, just moving around. I'm trying to find a big file. So yeah. If I go cat, hide, dim, integration, that's like a lot of stuff. Like sometimes when you're looking around through files, you don't want to see everything. So you might want to just do this. And it just gives you the first couple of lines. So usually that's enough to go like, oh, what is this thing? Similarly, another thing you might want to do is tail, where it just gives you the bottom n lines. And you've got an optional argument for doing that. What else do I want to say? So if you want to remove stuff RM, this is used with caution stuff. I could do completely something really bad that makes the rest of the lesson hard to do. So if you want to remove a directory, remdir, copy and move. So say I've got this file called thingo. I want to copy thingo.jl to thango.jl. Now if I look, There'll be a thing called thingo and a thing called thango. I don't want thango anymore, so I'll get rid of that. Yeah, copy, and you can also move. So it's a different thing between like, do you actually want a new thing to be written or do you just want to move it? There's lots of different things you can do. Yeah, you get the picture versus copy or move if you want a copy to stay in the same place. Using it to rename. Interesting thing with all these little things is that they're actually little programs themselves, and they'll have lots and lots of arguments that you would never guess. Minus help. So if you want to go similarly to how I do the shift question mark in Julia and go like type the function name, for most of these things, they'll actually be quite well battle tested programs that have been like used forever, and they've thought about the API really carefully. There'll be lots and lots of arguments for these things that you may or may not want to use. You can do colors and directories, blah, 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 blah. So useful one will be minus help. Sometimes there's also man. You can type man for this thing and it'll give you the manual. Minus help usually works. Another useful one, I guess, what do I want to say? Echo, print something to the screen. So echo, hello. It says hello back. Surprisingly useful for when you've got a variable and you want it to get printed to the screen. I find this one funny because I've got a stupid sense of humor, like an old man. It's like dad joke for me. It's like the only one where minus help doesn't work because it just says help back to you. So it's like your best friend when you're in trouble, you go like help, and they just go, oh shit, I don't know what to do either. I don't know. That's like a dad joke, but we'll go with it. Okay, talked about cat, just prints the text file if you want the first 10 lines or the last 10 lines. More useful is this one, diff, what we're going to talk to in Git. So, see if I got this open already, but we'll go with it. I just did source. Don't want that. Okay. So I've got two text files in source. It was in source. So I have this one called intro. It was a dark and stormy typo. Then I've got the same one. It was a dark and stormy night. Really useful thing is this one called diff, where, what were these functions called? What were these files called? We've got intro. Oh, they're not there. They're in source. Diff. So I've got these two files and I want to go through line by line and compare where they're different at each line. So that's this thing, diff. So it gives this kind of like 7C7 kind of not human readable thing, but this is more for programmatic use of diff. Again, if you want help with diff, minus help. You can probably understand if you're thinking through this, compare files line by line with a bunch of arguments. There'll be some stuff about display if you want to show it more for like people or more for programs. But I hope you can recognize that this is not a super simple problem to go like, if you're going to say the diff between two things, there's a difference between new line. Yeah, that's definitely a thing you could do. So I put a new line there. I don't know if it'll recognize it, but yeah, it does. Yeah, something's different at the end there. So a new line in the middle. Yep, that's another thing. You can just show it by doing it. So, yep, it's coming up with, there's a difference here. You have to learn to read the code, but going like in one, there's a space, there's a new line, in the other one, there's a not. You can imagine this gets really complicated for something stupid like this that's just going through line by line to figure out exactly what you meant to be different between when you were typing like source code. It doesn't understand source code. All it understands is going through line by line and going, what's different between these two things? And that can lead you quite astray with Git, because we'll talk about Git in a second. I guess they're kind of the basic commands. Grep's super useful. Grep is when you're looking through a file and you want to go like find instances of a match. That's like one you use all the time when you're going through source code stuff. Like, give me all these things. There's like a bunch of crusty old text editors if you really like that sort of thing. I forever used Vim. I didn't, before VS Code, for years and years, I used Vim. This guy's a bit funny because it's like, it's a modal text editor. So if I go here and I start pressing keys, like nothing really happens. So if there's like, but there's special things. So if I want to do a match, I've got built-in things for finding where does this word occur and then where does and occur. I can jump to those bits in it. Then if I want to edit it, I have to go into a different mode by shifting Shift I, sorry, and you'll see there's this insert thing. Now I can start typing. And if I want to get out of this back to editing mode, I have to press escape. And then if I want to get out of the program, I have to go escape, quit. And it go, oh no, it won't let me do that because you wrote something. So you have to go escape, right, quit. Then it will let me quit. So it's kind of this thing. It's like, it's infamous of like people getting stuck in it the first time they use it because I can't work out how to quit. But this is kind of where it came from. This is like back to the days of like having these modal editors make sense when you're on terrible network. That's why they were like that. Because like you kind of want to do a bunch of stuff in one go and then write it. And you want to make sure you meant to do that. Yeah, everything's better nowadays. So you got VS Code. Not everyone's using VS Code. I'd kind of half recommend it, but they're just it's just a text editor. Most of the time you're working with source code, you're just mucking around with text files. We're talking about ASCII encoding and Unicode encoding. They're just files with new line characters. That's all they are. So you can actually do it in whatever text editor you want. Nice thing with these things, I would say for VS Code is when you get the plugins. What do I have installed? I don't have a lot. In this one, I've got some, this basically, I don't use this program for anything but this course. So I've got some Julia, I've got a hex editor. I've got Docker there for some reason. I don't know why I did that, spell checker. But you know, if you compare this guy, I'm doing high dim int versus Vim high dim integration. I do get a little bit of code editing, code syntax stuff because I added a plugin for Vim for this guy. But you know, these editors are going to be a lot more friendly and help you with stuff a bit more. So you'll see this is a function. It knows enough about Julia with the Julia extension thing to go, this is a function and highlight it differently. If you're working with more normal languages, more regular languages, they'll give you more help. So like if you're working with something like TypeScript, and it's a Microsoft product. So yeah, you'll get lots and lots of help there. Has anyone used any more sophisticated editors? I mean, IDEs?
If I say our studio as more sophisticated,
yeah, yeah, it is definitely. RStudio is definitely a much better thing, and it's more integrated environment, so you can do your plotting, and you've got a, yeah. Sorry, MATLAB, yeah, it's true. Yeah, JetBrains stuff is kind of amazing. Like if you're working in Kotlin or Java or something, or PyCharm even. I think PyCharm's, yeah, PyCharm's okay. Yeah, so like there's all these things where they're much more integrated. Like if you get like a Java development environment, it kind of just feels like you press tab and it writes the code for you. It's kind of bizarre. But anyway, more set up depending on the language. Julia is easy enough that you'll get by with something like VS Code. Yeah, having a more integrated environment is definitely a thing. Basically, all I ever do, my day job, is I can start a terminal in here. Underneath, I can include stuff. That tends to be my typical work pattern. Cool. Where did I start with that? Oh, Vim and Emacs, if you want a polywar between those two. Sorry? Vim, for me. Because I learned it first. I think that's just the way it is. It's like you tend to like the one you learned first. I learned Vim. I never bothered to learn Emacs. Yep. Things can be piped into other things. So like, this is actually the powerful bit of Unix. If I go echo hello, into test.text. Might not seem it in this way, but if I go cat test.text, oh, come on. There'll be hello in there. So like you can chain these commands one after the other, and that's actually the more powerful thing with Unix. Okay, useful thing. Has anyone killed their computer writing a bad Julia program yet? Have you had anything run out of control? And yep, what was your strategy? Turn the whole thing off and off again. So is it process monitor in Windows is probably the thing to watch. Task manager, yeah. The Linux version of this is this thing called top. And we can see like, here's a bunch of processes running on this thing. You can notice that there's this thing that's thrashing my CPU and it's called Zoom. And it's got this process ID. I won't do this because it's probably bad for the lecture, but I can get this process ID, run kill and kill that thing. That's probably like one of these niceties of running in Linux where you can go, if your program's out of control, just look for all the Julias and go like, yeah, you die without your whole thing going out of control. Memory usage is more troublesome. We were talking about that before. Like if you're actually eating up all your memory, depending on how your system's set up, you'll start writing to the hard drive and swapping and everything will get really, really slow. So it's another thing. So a lot of my day looks like this, where I've set up top to sort by memory and I'm watching this memory monitor. And if it gets too big, I start killing things. So I'm in the same boat as you. It's like I do the same thing every day, right? Horrible programs and then have to kill them and before they take out my computer. I think I had much more to say about that. So yeah, you can kill this. I won't demonstrate that because I've had it go wrong. Some stuff for getting stuff off the web. There's curl and wget and SSH. SSH is super useful. I use that all the time. That's having a shell session on someone else's computer. Has someone been setting up GitHub and have they done for the, whatever they call the password these days, or SSH keys? Which way did everyone go? You went SSH. I would recommend SSH. It's a little bit more setup, but it's kind of easier. The other one's just a password that GitHub gives you. So like whatever. Okay, so yeah, so that allows remote access to other machines and some stuff. I think, yeah, saying about Unix philosophy is useful for you guys because you're starting to be programmers and making complicated programs. So inventor of Unix pipes, this guy, Doug McIlroy, says these things. So make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. This will seem more like sage advice the older and more experienced you are, but just like simplicity and composition is the way to make complicated programs. Like when you're starting to build bigger programs, complexity can go out of control really, really quickly. You probably would have seen this, like you do a thing and you fix it and it breaks and you're trying to add things to fix the thing and it gets worse and worse. It's like some sort of radical simplicity is the way to approach all this stuff. When you're writing programs, expect the output to become the input to another one and don't clutter it with crap. Don't expect there to necessarily be a user on the other side of this stuff as well. So it's just like, I'm just going to take stuff and run with it. Yep, this one is like most applicable for you guys with homework is like, just try and do it early and iterate on it. Like just keep grinding away at problems quickly, try and get in quickly and change. Yeah, try it early and fail early is a good way to do things. Don't try and think things too much. Just like part of this is learning by doing. I always think there's like a non-negotiable amount of suffering when you're learning to program, that you have to do these things. It sucks. And it's like, just try and try and try. Don't get downhearted is the biggest bit of advice. And making tools is like the sign, like this is more for when you go to get a job. But when I'm interviewing someone for a software engineering role, it's like someone who makes tools to make their job automatic is what I kind of look for. Like if you can automate things, and it's an advice for like, I guess for life, if you're trying to learn to program, is like, think about tools, think about things you might want to automate that you do every day, like make little applications for yourself. It's like a really good way to learn, particularly if you get, I'll talk about that later, but if you get really nerdy about a particular thing and that's a really great way to learn to program. Cool. Okay, Git. I think I had to show the obligatory XKCD comic for this one. So I'll let you read it if you can read it. Is it too small? Cool. Anyway, finish that? Okay, yeah, so it's basically a bunch of magic spells in the end. It's a cool thing that most people don't know how to drive very well. I would include myself in that. I don't know all the bits of Git. Has anyone had a go at using Git yet? Who's a beginner? Who's an expert? We go for beginner. Yeah, expert. Oh, I didn't even put my hand up. It gets famously, like notoriously hard on people to learn. Like the learning curve's really steep, so don't beat yourself up. There's patterns you can use, and I'm not going to show you anything too sophisticated now, but maybe it'd be good if Claire or someone later down the track gave you the more sophisticated workflows. The idea of Git, like, yeah, it's infamously bad. Like everyone hates learning Git, but it was so much better than everything that came before it that like it just won by virtue of that. Everyone would be familiar with this thing of like you're writing an assignment and you write the version and then you go, cool. And then you go to add some stuff and you go like, oh, but I don't want to write over my bad copy of the assignment. I want to make a new copy that's got like version 1.0. And then you go, oh, no, then I'm going to take a bit out of that one and I'm going to add some more stuff. So this is like version 1.0 final. And then you go, oh, and I'm going to edit that again. And I get up with this essay number 2 final. Has anyone done that or is that just me? Yep. So Git's meant to be to help you with that. That's the whole design of Git. Keeping track of software history over time. So this is a huge problem. So like we're people and we're fallible and we're going to make stuff and break stuff as we go. So an ideal software version control system would let you keep track of history over time. And ideally you could jump back to a previous point in time, you know, because if you're like me and you break stuff constantly, you make stupid mistakes and then everything doesn't work and you want to cry, and that's kind of normal. So Git's trying to help you. You want to be able to make, track, and merge experimental functionality. And this is this thing of like having the final. Like you've got the good version that you go like, yeah, this is pretty good, but I want to just make it faster by doing this one weird thing. I don't want to break everything and lose track of it at the same time. So these are kind of like desiderata for a version control system. It's like, I want to be able to do all these things. Keeping a remote backup of the source code in case of a disaster. This, I guess I would guess, but I'm old, is like, this is less common now than it was when I was younger. Has anyone lost a hard drive and like lost something super important? I know someone who was submitting their PhD thesis when I was younger and they got their laptop stolen out of their car and the whole thing was gone. They had no backup. So we're in this world now where like you'll have a shared folder on the cloud and like everything gets kind of done. These kinds of things where you got track changes on, you know, didn't used to exist and it was terrible. Now this is the one where I'd say Git fails, but it's pretty good. It's better than everything else. Allow teams of people to work on a code base without treading on each other's toes. And I said too much. You'll get frustrated. You'll have merge. Has anyone had a merge conflict yet? Yep. You did one? Yeah, you had a merge conflict?
Yeah.
How did you?
I think you have an option to select which one you continue with.
Yep.
Right?
Yeah.
We did just
Yeah. That's the one that'll make you want to cry, is when you get this merge conflict and you've got to deal with like, I'm changing this file and my friend's changing this file and we've changed them in incompatible ways. We're going to try and ask Git to splodge them together and it goes, I'm too dumb. And you get it back and you go, I'm too dumb too. So yeah. So there's lots and lots of source control things through history. It's like the early days of computing was literally what you probably did with your assignments, where you go final, and you just change the file name. That's kind of inefficient. Like you're saving a whole copy of this source code into a new spot with a new name. You've actually doubled the amount of memory you have to use. So I'll talk a little bit about that later. So Git was, again, I've said this guy's name, distributed made by the original guy was the Linus Torvalds was the guy who made Linux. So he was probably so frustrated. This thing I said about the best developers make tools. He was so frustrated making Linux and people trying to handle patches and stuff that he just made a version control system while he was making this other thing that's enormous project to deal with the complexity of having multiple people working on a code base. One of the weird things about Git, I don't think there's anything here. One of the weird things about Git that's like really hard to understand is it's actually distributed. If I say centralized versus distributed, does that make sense? Or is that like require more explanation? It's like every Git repo is fine. It's its own thing. The problem comes when you're trying to merge two different Git repos back together. So it's actually designed in this kind of really sophisticated way to be a distributed database of the source code. So like everyone's got their own version of it. So if you're worried about this fault tolerance thing, like back in the day of like one version of those goes away, everyone else still has theirs. So that's really cool. That's actually very hard to keep synchronized. And this is why people get in trouble. So that's the thing, the way it works. I don't know if I want to say too much about how it works, but this thing of like, it's super wasteful to keep every version of, yeah, I'll just do this one. This will actually work. It's super wasteful to keep every version of the file with a new file name. So maybe a useful thing is just to do the deltas, so the differences. If I just store the differences between files, that's much less because I'm a person writing in a file editor. There's only so many characters I can change per hour. We'll see, but yeah, you know, it's actually pretty small. Usually the deltas are really small. The problem is how do you calculate the deltas between two text files? And the fundamental mechanism is the same as this diff I was talking about before, where you go through the files line by line and you see where they've changed, and that's what you save. So what Git is doing under the hood, roughly, is because it's a distributed database, is it takes, when you first make the first thing in the repo, it stores the full version of that. And from then on, it takes a cryptographic hash of that thing. So you go like, this is what it was. Then it does a cryptographic hash of the deltas. So the Git tree is this like chain of deltas. So a hash, if anyone's not heard of that before, is a function that's kind of like, what do I want to say? It's like a pseudo-random ID for that file. So like if you pass it through the hash function, that's what you get. Cool. So what do I want to do? So I think I said about, I've got my Paul Silly Git repo. There's some basic commands you might want to do. So git status, this is a Git repo. And you'll see a bunch of stuff come up. So it says, I'm on branch main. Your branch is up to date with origin master. So this is a little bit confusing. So there's some idea of there's an origin for this guy that's somewhere else. And this will come up with why we worry about GitHub itself. Changes not staged for commit. It's got these things where I'm tracking this stuff. It's gone, this guy's been modified, this guy's been modified, this guy's been modified. And there's something in here that I made that's not tracked yet. So this is this, I just made this test.txt that had something goofy in it. Hello. Cool. So I'm not interested in this guy. Discard changes, or cheating by using the VS Code plugin. But yeah, so git status. Yeah, you'll also notice that the programming course itself is a GitHub. Has anyone gone and looked at it on GitHub yet? Yeah, this is a Git repo that I've cloned locally. Git status. Up to date with origin main. This thing of like, you want to see the history, you might want to do something like git log. And this thing I was saying about a cryptographic hash, this is like a special code for the changes up to this point. We'll say commit, blah, 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 head, main, origin head, author, Yoni, week 2, Tuesday, blah, blah, blah. Yoni did some stuff, and we can go through the history. And each one of these has a unique hash based on the contents of the change. Probability of these two things colliding is so small that it's not even worth thinking about. And you can go through and you can go to any point in the history and go back. Why is this not quitting? Okay, cool. That's basically Git as a conceptual thing. This thing about centralization versus distributed things. What's the first thing people get when they have something distributed? They centralize it because nobody wants to go all over the place and find all the things. So GitHub and Git are two different things. Git is a program, you can just run it on your own computer. You don't have to worry about syncing it up to anyone else's stuff. GitHub is like the golden blessed version of this repo that's somewhere else that we're going to keep for this remote backup. And the original version control systems like SVN, which was like the first one I learned to use, was like actually just a database. And it had a central version of that database. By consequence of that, the way they engineered it was really badly and everything was really slow. So like merging changes in took forever, branching took forever. Git was super fast. Does everyone have a GitHub account yet? Yep. Anyone not have a GitHub account? No, you're all on top of it. So this is mine. You'll get all these things. That's me. You see that I'm an open source vampire, that I never actually do anything for anyone else. I just take it all and use it for making money like an evil person. You can see that, oh, I did something for this course. So go over to here. There's this programming course with Julia. What did I do? You'll see pull requests. Some ones there's one there for me. Update lecture 2. So I think I talked about this in the lecture. I said at which and code LLVM don't work in an interactive session, need to run active utils, blah, blah, blah. So this is a hosted Git repository somewhere else that we're using as a backup. It's just a way of working with Git repos. So GitHub, keep those two things in your mind and always in your mind that you are sort of responsible for keeping these things in sync with each other. They're two different things and they're distributed. This is where everyone trips up. So this change, if we look at one of the things files changed, I'll do it here. Maybe this will work. We'll see if this works. So it says in markdown lecture2.jmd, there's this at line 643. So this is the diff thing I was talking about. It's going like, oh, there's a new line here saying using your interactive utils before which square root 2. So that's at line 463. Where's VS Code? So if I go code, I don't want to cause some freaky recursion. What is that? Control C. CD ... Programming with Julia systems course. CD, was it Markdown? Code dot. So this would be in lecture 2. I think that's what we said in here. So lecture unit 2, we go to lecture unit 2, go all the way down to line, do you remember what it was? 400 and something? 463. See, my version doesn't actually have that. So that interactive utils is missing from my version of this code. So the one I did it on my work computer. That's why not this computer. When I was doing the change, I went sneaky in my lunch break, go and fix the notes. This one, and I haven't synced this one up with the remote version of this repo. So it's not here yet. This is where this thing of like, you got to keep them in sync. So terminal, new terminal, get status. So I'm on branch main. In the olden days, it used to default to master, but like it's got like for people of color, it's got associations with slavery and stuff. So everyone's changed it over to main. If you talk to someone old enough, they'll start saying master main, like in a confused way. I still do that sometimes. So that's kind of, everyone's gone to main. Branch is up to date, but not really. It's lying to me a bit. Git pull minus rebase. This is one of these magic spells you learn. We'll see. We'll see that something in unit C, GitHub's IDE, Unix, GitHub IDE, IPython, there's this IPython notebook thing came along. And one line in Markdown Lecture 2 came in from the remote. So there we go. It's turned up now. Cool. So that's basically what's going on. So yeah. So most of the stuff you can do in, if I go back to the code, let's see what I can do here. It lies. It just knows its current state. I don't have it set up to automatically sync. It only syncs when I tell it to. So as far as it knows, it's up to date. It's lying to me though. Yeah, most of the stuff you would do, you can actually do in here. So like if you want to be naughty, I don't know if you guys can do this. You probably don't have the power, but if I want to go to Lecture 2, I can actually, nowadays you can actually edit this file. If I go over to that one, can you see where I can go to edit this file and say we go back to this 463 and I go like, I don't actually like this guy. So here, say like, it's driving me crazy that there's no space there, right? So I pressed enter, I've made a space. I can go commit changes. So Git is kind of like one of these modal things where you make a change, then you tell it you've made a change, and then you log it. There's a couple of steps to do this. So if I commit that change, commit message update lecture blah, there's options here for committing directly onto the main branch, which is naughty, but you guys should all probably do that to start with. What you really want to do is go, I'm going to make a branch and I'm going to get someone else to look at this thing and then I can bring it back in, which is merging back into master or main. I won't do this. Create a new branch and you could call it whatever. So most of the functionality is in the GitHub UI. What you really should be doing though is back here, you're going to go like, I'm going to make this change, save it, and then I'm going to go git status, and it's going to go, okay, change is not staged for commit. It's because there's a difference between lecture 2, and so the command here is git diff lecture 2, and it will do similar thing where it's gone like, oh, okay, there's a little plus there. So this diff thing is going like, oh, you've made a change there. So good thing about Git is it will tell you what you need to do. So if I go git status, it'll go change is not staged for commit. Use git add to update the file that will be committed. So I'm going to go git add lecture 2 git status. And it goes, okay, you've made this change. You can restore it. If you've done a silly thing and you actually don't want to commit that, you can undo it at this point. Otherwise, you can go git commit. And then it pops up, as I was saying before about these crusty editors, here's a thing called Nano that's come up to confuse my day. This is another one of these weird old editors. It's going to go like, please make a commit message for your changes. Line starting with hash will be ignored. Empty a message aborts the commit. So I wanted a space. It looked ugly. And then we're going to write. Oh, what is it? Control, right? Oh, shift, right. I'm having trouble. I've forgotten how to drive Nano. Ah, yeah. I didn't change my editor. I've forgotten how to drive Nano. Okay, Control X. Yes, sorry. There we go. Sorry, Nano problems. But basically it pops up an editor. This is actually configurable within Git. And then you say git status. It will lie to me again and say on branch main, you're ahead by 1 commit. So my branch is ahead of what's ever on GitHub. This is kind of hard to keep track of in your head. So there's a bunch of tools for visualizing this stuff about where you're up to and what you've changed. I use one called git k. that will make a little graph where it goes like, okay, mains here, SSH attestation and get config links. Yoni's done this stuff. This was my pull request before. I made a branch. I merged it back in. This branch is changing. And then there's this little one here. I wanted a space that looked ugly where it's added the plus down here. Cool. So that's kind of like me badly driving Git, mostly having problems with Nano. Visualization is a huge problem, and keep in your head all the time that like, just because I've done it locally doesn't mean it's going to happen in the cloud. I have to force that stuff to happen. I'd recommend the Git plugin. So this guy over here, I haven't opened the folder. You have all the source control stuff you can actually do in VS Code too. It's part of this thing of being an integrated development environment. I would thoroughly recommend, if you go back to the notes, can't remember whose cheat sheet this is. Atlassian, Australian company, done good. This guy, most common commands, and there's like a million tutorials, which is a sure sign that it's problematic for using Git. So useful stuff is like, I want to create an empty repository. I want to clone something off the internet. You'll notice that if you go to the courses. I'll get back out of this. Okay. If I go back to programming course, if I go code, click on this guy, Control C. If I want to clone this repo, so pull it down from the remote, that's one of the more common commands. Git config is the one you're going to actually have to do. Is like when you're setting Git up, you have to say who you are and what your email address is. This is like the first thing you have to do. I think if you see mine, Git config list. I always have problems when I do this stuff that I'm going to do something insecure and like everyone's going to see my SSH key, but this should be fine. You'll see like my username is Paul Billette. My email is paulbillette@gmail.com. Whatever. The origin URL is this programming course at GitHub. You can point this to other places, like you can host your own repo somewhere, you can point it there. But most common will be something like this. Blah, blah, blah. A little bit of stuff about what to do. Most important one for you guys is number 1 and number 2, where you want to set your username and email address so you know who it is. And if you don't like someone, you can set it as them and no one will ever know. Yeah, this little workflow I said before of add, commit, status, log, and diff. This is when you're getting into trouble of undoing changes, revert, reset, clean. Rebase, don't worry about this stuff yet. That'll come up in the future. Branching and merging, it was one I definitely recommend though. So like if you've got a good version of the homework and it's working and you want to try something weird, make a branch, leave that one alone, do all your stuff over here. When it's good, bring it back in. Cool, that's like a really quick whirlwind thing of Git. Yeah, there's so much going on. Big one with Git is like, it's not for storing passwords. Please don't store passwords. It's like if your stuff's open, you wouldn't believe like how many robots there are crawling GitHub looking for things that look like passwords. So like if you have your SSH keys or something, do not put it anywhere near your source code repository. Git's only really for text files. So like it could be really appealing to put like an image in there, and you probably will for your homework, but tracking that initially is going to be problematic because like every time you diff it, like if I change 1 pixel in an image, the diff is going to be the whole image. So your Git repo will get big really, really, really quickly. So Git's only for text files because of this diff mechanism. So that's another one. So yeah, keep it well away from passwords. It's got to be a little bit careful because there's lots of bad people on the internet. It's for source code, not really files. And that's what I'd say. Cool. Hopefully that's enough to get you started. That's just hassle me if you've got a problem with this stuff. It's like, everyone's had these problems when they learn. Okay, thank you.